Welcome to Study Loop.
This is the answer to Chapter 22, problem number 8 from the Smith Organic Chemistry textbook. And for this problem, we're given sets of data about two different molecules, and we are asked to use that data to identify the molecules. So, starting with A, the first piece of information that we're given is the molecular formula. And in a problem like this, where you have an unknown molecular structure and you're just given pieces of data, I think that it's always best to start with the molecular formula. And you can use the molecular formula to calculate the hydrogen deficiency index. And the hydrogen deficiency index, if you remember from earlier chapters, tells you how many rings and or double bonds a molecule has. And so without nitrogens or halogens, the simplified formula for calculating hydrogen deficiency index is 2 times the number of carbons plus 2 minus the number of hydrogens, and then all of that is divided by 2, and that gives you your hydrogen deficiency index. So for molecule A, we have 2 times 9 carbons plus 2 minus 10 hydrogens, all of that over 2, and we get 5. And so whenever you see a hydrogen deficiency index of 4 or more, you should probably right away think aromatic ring. So an aromatic ring, remember, is going to account for a hydrogen deficiency index of 4. The ring itself counts for 1. The 3 double bonds in the ring count for 1 each, for a total of 4. So for a problem like this, where we have an HDI of 5, that makes me think that we have a ring, and then somewhere else we have a double bond in the molecule. And so from there, I would move on to the IR. IR is good in this instance because it can identify some functional groups for us. So the first piece of IR data that we're given, 2895 to 3091 wave number, that is really just telling us that there are sp2 and sp3 carbons in this molecule. And if we look back at the assumption that we made based on our hydrogen deficiency index, which is that that assumption was that we have an aromatic ring and somewhere else in the molecule a double bond, this IR data makes sense because that would be our CsP2 hybridized carbons. And then also this second piece of IR data, 1743 wave number, is a carbonyl carbon-oxygen stretch of some kind. And so, so far, everything that we're seeing points to an aromatic ring and a carbonyl somewhere in the molecule. So lastly, we're given NMR data. And I think that the way to interpret NMR data is to look at it one piece at a time and try to identify functional groups or pieces of the molecule that each piece of data is describing. So 2.06 ppm singlet that integrates to 3 protons, that's pretty clearly telling us that there's a methyl group in this molecule. The integration of 3 is a big hint. The fact that it's a singlet tells us that it has no neighbors. So right away, if I'm already thinking I have a carbonyl in this molecule, I'm now thinking that this singlet is attached to one side of this carbonyl. The next piece of information that we're given is another singlet. This one only integrates to 2 protons, and it's pretty downshifted. It's shifted pretty far downfield. 5.08 is a pretty good shift. It means that those protons are in a very electronegative environment. So that to me says that we have a CH2 group and that it's connected to one or more electronegative groups. And lastly, we have a signal with a chemical shift of 7.33, and an integration of 5. And right away, this tells me that this is a monosubstituted aromatic ring. Whenever you see something in the region of the high 6s to mid to high 7s, and an integration of 4 or 5, you should be thinking aromatic ring. And this is handy because this tells you how substituted the aromatic ring is. An integration of 5 tells us that we have a monosubstituted aromatic ring, because just a benzene ring would have 6 protons, so it would integrate to 6. So when you see a signal in this region with an integration of 5, you know that it's monosubstituted. Similarly, a signal in this region with an integration of 4 would tell you that you have a disubstituted ring. So when you put all these pieces together, you get this molecule that I've drawn up here. And there is some question as to how do you know that the methylene group, the CH2 group here, and this oxygen here are where they are. Why couldn't they be switched? And they could be switched, but again, looking at this 5.08 shift for this CH2 group, that's pretty significantly shifted downfield. And so that to me is suggesting pretty strong deshielding based on being in between this aromatic ring, which is going to cause deshielding, and this oxygen, which is going to cause further deshielding. And if the oxygen and CH2 were switched from how I've drawn them here, I would expect it to be a little less downshifted. I would expect it to be maybe 3.5, maybe 4 ppm. Instead, it's at 5.08. And so that's how we arrive at this answer. For B, since this is already sort of a longer video, I'm not going to talk about everything as in depth, but we follow the exact same steps. So we get our HDI. Our HDI is 9, which is a pretty high HDI. So again, I'm thinking 2 rings to account for 8 of that, and then a double bond elsewhere on the molecule to account for the 9th degree. The IR, again, telling us we have sp2 and sp3 hybridized carbons in the molecule, and telling us, again, that we have a carbonyl. And then looking at the NMR, there are only 2 signals this time. So we have a 5.35 singlet for 2 protons. Again, this to me says CH2 group. And then we have between 7.26 and 8.15, we have a multiplet that integrates to 10 protons. And so I think that that is 2 rings at 5 protons each. And so again, you put all of that information together, and this is the molecule that you would come up with. And again, if you wanted to argue that this CH2 and this O could be switched, I would say for the same reason as I said in A, that I don't think that that's possible, because again, 5.35 is shifted significantly downfield. And if the CH2 and the oxygen were switched, I think it would be more upfield. And so this is the correct answer. And that is the way to solve this kind of problem. These kind of problems are great. They pretty closely mimic what an actual experimental organic chemist would do if you had a molecule and you didn't know what it was. And for that reason, I think that they're very worthwhile. And so that is the answer to chapter 22, problem number 8.